Hello everyone, my name is Grzegorz Dudek, I am from Częstochowa University of Technology, Poland, and my talk is on randomized neural networks for forecasting time series with multiple seasonality. After short introduction, I'll present the proposed forecasting model, then I'll describe randomized learning of this model, I'll show some experimental results, and I'll conclude the work. Time series expressing different phenomena and processes may include multiple seasonal cycles of different lengths. They can be observed in demand variations for various goods, weather conditions, customer numbers, and so on. Over the past years, many sophisticated forecasting models for time series with multiple seasonality have been proposed, including statistical and machine learning ones. The most popular ARIMA and exponential smoothing models can deal with multiple seasonality by including additional seasonal factors or components, but both these models have a significant weakness. They require the same cyclical behavior for each period. Machine learning models have the ability to learn relationships between predictors and forecasted variables from historical data. They deal with multiple seasonality differently depending on the model. One of the most popular machine learning approaches for time series forecasting are recurrent neural networks such as LSTM, which have ability to process sequential data and capture long-term dependencies. These all models rely on incorporating into the model mechanisms which allow to deal with multiple seasonality. An alternative approach is to simplify the forecasting problem by time series decomposition or preprocessing. In our earlier works, we used successfully pattern representation of time series, which turned out to be competitive with state-of-the-art hybrid models combining machine learning and statistical models. Encouraging by these results in this study, we use pattern-based approach, initially encoding time series to simplify the forecasting problem with multiple seasonality, and we propose randomization-based neural network to solve it. Randomized learning was proposed as an alternative to gradient-based learning, as the latter is known to be time-consuming, sensitive to the initial parameter values, and unable to cope with the local minima of loss function. In this study, to generate the random parameters, we used three methods recently proposed. These methods distribute the activation functions of hidden nodes randomly in the input space and adjust their weights to the target function complexity. The proposed forecasting model is composed of encoder and decoder modules and a randomized fit for a neural network. The encoder produces a new time series representation, that is input and output patterns of seasonal cycles. Randomized neural network learns on patterns to simplify the relationship between input and output data. Decoder transforms pattern representation into original time series using coding variables E bar and E tilde. The task of the encoder is to convert an original time series into unified input and output patterns of its seasonal cycles. To create input patterns, the time series expressing multiple seasonality is divided into seasonal sequences of the shortest length, expressed by vectors ei, where n is the seasonal sequence length and I is the sequence number. These sequences are encoded in input patterns xi as follows, where ei bar is a mean value of sequence ei, and ei tilde is a measure of this sequence dispersion. Note that x patterns are normalized versions of centered vectors ei. All x patterns representing successive seasonal cycles have zero mean, the same variance, and the same unity length. However, they differ in shape. Thus, the original seasonal sequences are unified. This is shown in this figure on the example of the hourly electricity demand time series expressing three seasonalities: daily, weekly, and yearly. This is original time series 4-year period. The fragments of this time series and representation by patterns X. Note that the X patterns representing the daily cycles are all normalized and differ only in shape. The output patterns, YI, represent the forecasted sequence EI plus tau, where tau is a forecast horizon. The Y patterns are determined as follows, where EI bar and EI tilde are the same as for X patterns. We use the same coding variables because the coding variables for the forecasted sequence, EI plus tau, are unknown for the future period. Using the coding variables determined from the previous period has consequences which are demonstrated in this figure. Note that Y patterns reveal the weekly seasonality. Thus, the Y patterns are not unified globally, but are unified in groups composed of the same days of the week. For this reason, we construct forecasting models that learn from data representing the same days of the week. The decoder converts a forecasted output pattern into a time series seasonal cycle. The output pattern predicted by a randomized network is decoded using the coding variables of the input query pattern X, using transformed equation for Y pattern definition, where E hat is the forecasted seasonal sequence, Y hat is the forecasted output pattern. E bar and E tilde are the coding variables determined from the time series sequence encoded in query pattern X. In this study, we consider a single hidden layer fit 4-on-1 network with weights A and biases B generated randomly, with M hidden nodes, activation functions H, we use sigmoids, and output weights beta. The output weights beta are determined using the Moore-Penrose generalized inverse of matrix H. H is a hidden layers output matrix. In our forecasting model, we have n outputs, n output neurons, so we determine a set of weights beta for each of them. The network expresses the set of functions phi j. Typically, the hidden node weights and biases are both generated randomly from the same symmetrical interval. This is not the best solution because the weights and biases have different functions and they should be selected separately. Recently, several methods for generating random parameters were proposed to improve the performance of randomized learning. The first one, RAM, selects weight A from interval -u, adjusted to the complexity of target function. Then the biases are determined in such a way as to ensure the steepest fragments of the sigmoids into input hypercube. The resulting biases are dependent on the weights and some point X star selected randomly from the training set. R alpha M generates sigmoids with uniformly distributed slope angles. This method first selects randomly sigmoid slope angles from the interval adjusted to the target function complexity, and then calculates the weights. Biases are determined in the same way as in RAM to introduce the sigmoids into the input hypercube. Data-driven method DDM first selects randomly one of the training point, X star. Then it fits the hyperplane to the target function in the neighborhood of X star, and finally it calculates the weights, taking the fitted hyperplane coefficients. We apply the proposed randomization-based neural models to forecasting hourly time series with yearly, weekly, and daily seasonalities. They express electricity demand for 4 European countries: Poland, Great Britain, France, and Germany. We use real-world data. The data period covers the 4 years from 2012 to 2015. We forecast the daily load profile for each day of 2015. The forecast horizon tau is 1 day. For each forecasted day, a new training set is created and a new randomized model is optimized and trained. Hyperparameters were selected using grid search and 5-fold cross-validation. Forecasting quality metrics for the test data are presented in this table. They are averaged over 100 training sessions. For comparison, we apply the multi-layer perceptron composed of a single hidden layer with m sigmoid nodes, whose number was selected using cross-validation. Distributions of average percentage errors are shown in figure 3. Based on these errors, we performed a Wilcoxon-signed rank test to indicate the most accurate models. Figure 4 depicts pairwise comparisons of the models. The arrow indicates which of the two compared models has significantly lower error. As can be seen from table and figure 4, the randomization-based networks gave significantly lower errors than fully trained MLP for each dataset. According to the Wilcoxon test, RAM outperformed the other approaches. This figure presents examples of forecasts of the daily load profiles. Note that the proposed models generate multi-output response, maintaining the relationships between output variables, that is, Y-pattern components. In the case of single output models, these relationships are ignored because the variables are predicted independently. This may cause a lack of smoothness in the forecasted curve. This figure shows the optimal numbers of hidden nodes selected in the cross-validation. Obviously, the number of hidden nodes is dependent on target function complexity. Small number of hidden nodes in randomized network, most often between 20 and 30, means relatively low complexity. Randomized network contains little more hidden nodes than MLP. The optimal values of smoothing parameters for the randomized learning methods are depicted in these box plots. It can be concluded from these results that the relationship between input and output patterns is modeled using relatively flat sigmoids. Note relatively small values of U and alpha max and high values of the neighborhood size K. Thus, for our forecasting problems, we can expect flat target functions without fluctuations. Such target functions can be modeled using RAM. Its competitors, Rα-M and DDM, reveal their strengths in modeling highly nonlinear target functions with fluctuations. Conclusions. Forecasting time series with multiple seasonality is a challenging problem, which we propose to solve with randomized feed-forward neural networks. Unlike fully trained networks, randomized networks learn extremely fast and are easy to implement. To deal with non-stationary time series with multiple seasonal periods, the proposed approach employs a pattern representation of the time series. This representation simplifies the relationship between input and output data and makes the problem easier to solve using simple regression models. The effectiveness of the randomized networks in modeling nonlinear target functions was achieved due to the application of new methods of generating hidden node parameters. These methods, using different approaches, introduce the steepest fragments of sigmoids, which are most useful for modeling target function nonlinearities, into the input hypercube and adjust their slopes to the target function complexity. This makes the model more flexible, more data dependent, and more dependent on the complexity of the solved forecasting problem. The simulation study showed that the forecasting accuracy of the proposed randomized models is comparable to the accuracy of fully trained neural networks. Thank you very much for your attention.